Hello, my Algebra 2 honor scholars. Okay, so this should be fun, hopefully. My first screencast of the year. We'll see if it's successful and continue on if so. Alright, so, we're getting into, we've kind of been reviewing a few new things so far this year, but now we're kind of getting into some fun things, the way I see it. So one thing I want to start talking about is the relationship between math and the rest of the world, and science in particular, since it's the study of the world. Um, I was always taught by my professors in college that biology is based on chemistry, and chemistry is based on the law of physics, and physics, of course, is the application of math. And so now perhaps these arrows should be going the other way, but we can see how all of life is ultimately based on math. Now I know all you guys have an interest in math, but I always found that interesting and the word problems that we do in class and whatnot, hopefully bring these math principles to life to see how we can really apply them. And so today we're going to start talking. Whoa, we're going to start talking about the three-dimensional world, and it has great implications in physics. And so I attached a couple videos for you to check out this evening. One by Carl Sagan, another just by some random high school dude that had some interesting things to say about the fourth dimension. But the Carl Sagan video. He's a very famous scientist. He's now passed on, but he demonstrated a little bit about the two-dimensional, the three-dimensional, and introduced the four-dimensional world in that video. And so in the future, I'll probably have my Algebra 2 students, the honor students, over the summer read a book called Flatland, in which he and that's something that's a book he was referring to, Carl Sagan was referring to. So some of you may have heard of it already, but I'll probably have my students read that over the summer in the future. I was assigned to this class so late in the summer that I wasn't able to do that, but it's very interesting. It introduces that flat world and that three-dimensional world, and perhaps the fourth dimensional world to us three-dimensional dwellers. So anyway, let's continue on and see how this applies to us. So we're going to, give me a second. There we go. We're going to talk about 3.5, which we've already kind of introduced, but some of you seemed a little bit perplexed by 3.5, which was graphing the linear equations in three variables. So as you're familiar, I'm trying to make some parallels here to demystify it for you. An ordered pair, x comma y, represents a dot in a two-dimensional world, perhaps there, x comma y over the x coordinates and up the y coordinate. And now an ordered triple simply represents a dot as well. But we're going to talk about this third dimension that's introduced. And so it's not only over sum and up sum, but it's over sum and up sum and out sum. Okay, so all right, moving on. These are solutions. These values in for x, y, and z are solutions of equations if the equation is true when the values of x, y, and z are substituted into the equation. Okay, so, well, let's see, let's make the xy, let's say it's 1, comma 1. the xy coordinate, that is a solution of a lot of different equations, but here's one example of the equation x minus y equals 0. And if we plugged in 1 and 1 and 1 for the x and 1 for the y, we see that that's true. So the point 1 comma 1 actually lies on the line x minus y equals 0, which is this line right here. And here's 1 comma 1 roughly, and we see it does lie on that line, and it is a solution. So the similar situation here, if we had 1 comma 1 comma 1, that would be true for some 3-variable equation, but we're going to get to that in a bit. But I just wanted to show you how we're going to parallel that. Now, instead of, you know how we talked about quadrants? We have quadrant 1, we have quadrant 2, we have quadrant 3, we have quadrant 4 in a 2-dimensional world. Well, in a 3-dimensional world, we now have things called octants. Now, I like to be consistent in math, of course, and I don't understand, we've talked about this in class, why we've learned it for 9 years or whatever, that x shoots to the right and y shoots up. Oops, sorry, whoa, what happened there? Y shoots up, going green, and then suddenly when we introduce a third variable, well, the drawer of this diagram seems to agree with me that it should remain x to the right, y up, and z coming out and punching us in the face. However, our book and some other mathematicians rearrange these axes into x coming out towards us, y going left and right, and z going up and down. And so in this situation, it's like we're hanging out in this part of this diagram looking down. We're looking down on this blue section. This green section is right in front of us. This green section is right in front of us over here. And this X and this orange section, I don't know if I have the color orange here. There we are. This orange section is actually to our left over here. Does that make sense? Okay, so this green section is in front of us, and the blue section is down below. Okay, so great. So I drew a little schematic myself to kind of show that. And what you can see is whether it looks like this is a better drawing because there's shading and highlighting versus my Mickey Mouse version. There are 8 octants. 1, 2, 3, 4 on top, and 5, 6 back behind a 7, and 8 octants on bottom. So, and this is how we name them. The first octant was all the one we're only gonna deal with. This first octant is the one where all the values are positive in this little space right here. So x is positive if it comes out, y is positive if it goes to the right, and z is positive as it goes up. So we can now, well, let's look at this version right here. this dot right there, it comes out a positive value x, it goes to the right a positive value y, and it goes up a positive value z, and there's that dot floating in three-dimensional space. Of course, we're representing that in a two-dimensional medium, so it's sometimes hard to see, but if you train your vision to come out, over, and up, now you know this dot is closer to you than this z-axis is. Okay, so let's just talk about how to graph something. So let's say we have something simple like 2, 3, 4. Okay? 2, 3, 4. Now there's several different ways we can go about graphing this sucker. So let's do one just like they did here. And then I'll show you maybe a more preferable method by yourself. So I'm going to change this to a blue. See if that will work. It's blue too. So it'll be color coordinated. So we can come out to here. Place a dot. There's a big, that's the x value is coming out 2 spaces. Now the y value is going to the right 3 spaces. So we can either come back to this origin and go over 3 spaces, or from this point we can go over an equidistant length. So let me show you one version. Let's go, I'm going to go red. Okay, so to get an equidistant length, I'm going to make a line that's out to 3 spaces. I'm going to take that line, I'm going to move it over here. Great, so that is from this point over 3 spaces. And now I can do the same with the z. I can come here, I can draw, whoops, no, I kind of want to do a line, don't I? A line, it's green. We're going to go 1, 2, 3, 4 spaces. Okay? Alright. And now I'm going to take that, I'm going to bring it over here and go the end of the red, I'm going to go the beginning of the green to the end of the red. This would be good practice for vectors someday when you're doing them in physics. And sure enough, here I'll make this purple. Here is the dot floating in space. Well, if that doesn't make any sense to you, then I really highly suggest this method. And I would love to see it if you did this on the test. So let's check out making actually a box. Let's make a box. And make it blue. Make a blue line this way. And then make a parallel line. 1, 2, 3, 4. I'm going to want to make 4 parallel lines. I'll show you how to do that. And now, hope I'm not going to run out of time. Bam, bam. Bam, and green line.